In this video, a Hello World example of supervised learning in artificial intelligence using multi-layer perceptron and backpropagation in CUDA is a follow-up of the MLP video we posted a month ago. Here, we visit the same examples, but implement them using CUDA. Billy will first give us a review of what we discussed last time.
Let's begin with a brief review of the perceptron, the simplest form of an artificial neural network and a supervised learning algorithm. The diagram illustrates a basic perceptron with inputs x1, x2, blah 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 xm, where x0 equals 1, representing the bias term, and w0 is the corresponding bias weight. Each input is multiplied by its respective weight, and the products are summed along with the bias term. This sum is then passed through an activation function, g, to produce the predicted output y hat. For example, the activation function g could be a step function. The perceptron's operation can be summarized by the following equation. To simplify the model, we treat w0 as the bias and set x0 equals 1, allowing the output to be expressed as the dot product of the weight vector w and the input vector x. The weights are updated based on the error between the predicted output y hat and the target, desired, output y. This error is multiplied by a small constant called the learning rate, and then scaled by the input to compute the weight adjustment delta wi. The weights are then updated by adding delta wi to wi. This simple perceptron can only learn linearly separable patterns, such as those of an AND gate or an OR gate. Linear separability means that a straight line can divide the data into distinct categories, for example, separating white circles, representing 1, from black circles, representing 0. While a perceptron works for AND and OR gates, where a single straight line suffices, it fails for the XOR gate, which is not linearly separable. No single straight line can classify the data correctly. To learn nonlinear patterns like XOR, we need a multi-layer perceptron, MLP. An MLP can distinguish data that is not linearly separable. A typical MLP consists of an input layer, example, with inputs x1, x2, x3. One or more hidden layers, each containing multiple neurons. An output layer, example, with 2 neurons. Each neuron in one layer is connected to neurons in the next layer via adjustable weights, enabling the network to learn complex decision boundaries. An MLP is a type of supervised learning model. Its operation can be summarized as follows. 1. Input processing. The MLP takes an input pattern X, comprising features x1 to xn, from a training set. This input is fed into the network, which consists of 3 key layers. An input layer receives the data. One or more hidden layers process the data through weighted connections. An output layer produces the final prediction. 2. Output generation. The network processes X through these layers, applying activation functions and weighted sums, to generate an output pattern Y. 3. Error calculation. The predicted output y is compared to the true target output yd, desired value. The difference between them is quantified using an error function, example, mean squared error, which measures the discrepancy across all training samples. 4. Backpropagation and weight adjustment. The error is propagated backward through the network, adjusting the weights between neurons using optimization techniques like gradient descent. This minimizes the error in subsequent iterations, bringing y closer to yd. 5. Iterative training. The process repeats with new input patterns from the training set. Over multiple iterations, epochs, the model's accuracy improves as the error progressively decreases. A common way to measure error in machine learning is by using the mean squared error, MSE. As shown in this formula, E is equal to 1, 2k sum from 1 to k, ed, square. We want to adjust the weight so that E decreases and eventually get to the minimal minimum. To improve the model's performance, we adjust the weights to minimize this error. A widely used optimization technique for this purpose is gradient descent. The core idea is to iteratively update the weights in the direction that reduces the error, following the negative gradient of the error function. For example, consider a plot where the error E is a function of a weight W. By computing the derivative, or partial derivative, partial E, partial W, we determine the slope of the error curve. Adjusting W in the direction of the steepest descent leads us toward a minimum of the error function. In many cases, gradient descent converges to the global minimum. However, if the error landscape is complex, such as having multiple valleys, the algorithm might get stuck in a local minimum instead of reaching the optimal solution. For simplicity, we'll assume a convex error function where only a single global minimum exists. So this is the formula that we need to adjust the weights. Delta W is equal to a constant times the gradient. Starting from this, after performing a series of straightforward mathematical derivations, we can arrive at the following algorithm that trains an MLP. So this is the multi-layer perceptron MLP with backpropagation algorithm. It works as follows. Here are the notations. The inputs are x1, x2 all the way to xn like what this diagram shows. x1 to xn are the inputs and we have the hidden nodes h1, h2 to them as shown here. Each node is a neuron. This is an input neuron, hidden neuron, and this is an output neuron, and each neuron has a value. Outputs are y1, y2 up to yk. The weights from xi to hj is wij, and from hj to y1 is wjl. We need an activation function, and the activation function we need here is a continuous function instead of a step function so that we can find the derivative easily. We use a sigmoid function which is given by this formula. It is 1 over 1 plus e to the power negative z, and the derivative of sigmoid, sigma dash, is equal to sigma z times 1 minus sigma z. So from this formula you can see that when z goes to infinity, this term is 0 as e to the power negative infinity is 0, so we get 1. That means this approaches 1 as z increases. On the other hand, when z is negative and goes to negative infinity, then this is infinity. As 1 over infinity is 0, we get a 0, so on this end. The derivative of a sigma function is given by this curve, so it goes to 0 at both ends as it is symmetric about the z equals 0 axis. Our simple MLP, the structure consists of 3 layers only: the input layer, a hidden layer, and the output layer. In more complicated cases, you can have more than one hidden layer, but here we just consider something simple. As shown here, a weight connects 2 neurons. Wij denotes the weight from the input node xi to the hidden node hj, like this one. So this will be w1, 2, and wjl represents the weight from hj tool. To distinguish this weight from this, we will add another index O to denote the output. So without an O we specify input weights, otherwise we specify hidden to output weights, or in this diagram they use the index 1 and 2 to distinguish the 2 weight sets. The first stage of the algorithm is the forward propagation, in which we compute the output of the network from the inputs. This involves several steps. In step 1, we compute hidden layer activations. Each neuron hj computes this, sum from 0 to nwij times xi. So this gives an aj for a particular neuron. We put this aj into the activation function g to get the value hj. Here g is the activation function, and we use the sigma function, which is 1 over 1 plus e to the power negative aj. In our notation, woj is the bias and x0 is 1. In step 2, we compute output layer activations. Each output node L computes the sum of the hidden layer activations and apply the activation function. So each of this node computes this hj value times the weight, and sum over j. To distinguish this weight from this weight, we add an O here to denote output. So it's sum over j here. Basically this means from the hidden layer to an output layer node L. YL is equal to GZL. WO01 is the bias, H0 is 1. Now we have all the calculated. We need to do the backpropagation. In this process, for each YL we calculate an error E, which is basically the difference between the desired output and the output YL from the MLP. We then calculate the gradient of the output error delta L, which is equal to EL times dash ZL. G dash is the derivative of G, or the gradient, partial G partial ZL. We also compute the hidden layer gradient error delta J, which is given by delta J equals sum from L equals 1 to K delta L times WOJL then times G dash a J. Then we update the weights. We adjust the weights from hidden to output layer by adding WOJL, a term of eta times delta L times HJ. Eta is a small constant, referred to as the learning rate. We also adjust the weights from input to hidden layer by adding to Wij the term eta times delta J times XJ. We iterate this process a number of times so that the error gets smaller and smaller. Now to illustrate this algorithm, or to implement this algorithm, we consider a very simple example. We will taunt an MLP to work like an exclusive OR gate. We discussed that an exclusive OR gate cannot be learned or trained by a simple perception, as the data cannot be separated by a straight line. This is the exclusive OR gate truth table. We have two inputs x1, x2, and this is the output. 0 exclusive or 0 is 0, 0 exclusive or 1 is 1, and so on. Basically, the exclusive OR is a mod 2 addition. So 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1, 1 plus 1 is 2, but 2 mod 2 is 0. The following is C++ implementation of an MLP to train the exclusive OR gate. Let's copy this program and paste it to a file and see how it works. This is a strict implementation of the formulas that we just discussed. So we have N1, the number of inputs, equal to 3. M1, the number of hidden nodes, including the bias, is 3. Note that M1 is M plus 1. K is 1, the number outputs. Num samples is 4, which is the number of samples or sets of inputs, 1, 2, 3, 4. These are the inputs for testing or for training the MLP. X0 is 1, as X0 is the bias. X1 is 0, X2 is 0, and 0, 1, 1, 0, 1, 1. The corresponding outputs we call the labels here are 0, 1, 1, and 0. That means the output for input 0, 0 is 0, for 0, 1 is 1, for 1, 0 is 1, and for 1, 1 is 0. These are random weights from the input layer to the hidden layer. There are N1 times M1 weights. WO holds the weights from hidden layer to output layer. These are M1 times K small random values. His is a simple class that implements the formulas, so we have this A, H, Y, Z, which are the same notations we discuss above. The A is this. The H is this H. The Y is the output. Z is the Z here. And here actually K equals 1, as we only have one output. To begin, we have a constructor that passes in the learning rate. We set eta to be the learning rate, and H0 is always 1, as it is for the bias calculations. This G is the sigma function, 1 over 1 plus exponent minus x. The one that we discussed here. This is the GD, sigma dash, the derivative of the sigma function. It is 0 equal to sigma 1 minus sigma. Here S is the sigma. So the derivative is S1 minus S. If you're passing directly the parameter s, and then this CUD line could be omitted. But for clarity we do it this way even though it takes a longer time. This is the forward propagation. We first calculated j by summing the products of wij times xi over I. That means for a particular hidden node j, we sum over all the input nodes I. We feed a j into the activation function to obtain hj. We do this only when j is larger than 0, as h0 is the bias, which is always 1. This implements the calculation of the ZL obtained by summing the products of WOJL times HJ over J. We feed ZL to the activation function to obtain the output YL. We return Y, which is a pointer pointing to an array containing the outputs. And this is the backward propagation algorithm. Again, it is a straightforward implementation of the formulas. We will calculate the delta J for the hidden layer, delta OL for the output layer. For the first part, we calculate the delta L from E, which is the difference between the desired output and the predicted output, the output that's given by the MLP. Then we multiply this to the gradient of ZL. You can see that this is the straightforward implementation of these formulas. Delta OL is E times the gradient of ZL. We then calculate delta J for the hidden layer, which is the sum over L of the products of delta OL and WOJL and the gradient of a J. Then we do the updates, which are straightforward implementation of these formulas. In the train function, X will point to the first input data set via the getInputData function, and YD will point to the corresponding targeted output data. We first call the forward propagation function and then the backward propagation function. We do this for the different input samples and repeat the process for epochs times. Member function print weights is to print out the weights for reference. And this is the destructor. We have an external classifier function because the values that we deal with are doubles. So we classify them to be 0 or 1. If x is smaller than 0.2 and larger than negative 0.1, we return 0, meaning that it belongs to a 0 in this range 0.8 and 1.1. We classify it as 1, otherwise it fails and the function returns negative 1. In our example, we use the learning rate or eta of 0.5 and train the MLP for 10,000 times. This is for testing. After training, we try to test the trained MLP. Let's compile and execute the program. It executes. You can see that we get what we expect. 0 exclusive 0 is 0, but the actual value of this value returned from the forward prediction is 0.02, so we classify it as 0. For this one, actually the actual output from the MLP is 0.98 and is classified as 1. 1 exclusive or 0 is 1, 1 exclusive or 1 is 0. To implement this in CUDA, we organize the computation into 3 groups of threads. Input layer group. This group handles the input nodes and requires N1 threads. Hidden layer group. This group is responsible for the hidden nodes and uses M1 threads. Output layer group. This group processes the output nodes, with K threads allocated. The threads can be defined by this command: dim 3 threads N1, M1, K. The thread indices are utilized as follows. Thread ix.x indexes the input nodes, thread ix.y indexes the hidden nodes, thread ix.z indexes the output nodes. This is the complete CUDA implementation of the XOR multilayer perceptron, MLP. It closely follows the structure of the C++ implementation presented above, but requires certain functions to be defined as CUDA kernel functions for parallel execution. The D forward kernel performs forward propagation. In this function, K denotes the KDH input sample. W stores the weights from the input layer to the hidden layer. WO stores the weights from the hidden layer to the output layer. H, A, and Z correspond to the hidden activations, pre-activations, and output layer pre-activations, respectively. as used in the earlier formulas. Y is the array of predicted outputs, which will be used in the backward pass. The D backward kernel handles backward propagation and shares the same function signature and argument structure as D forward. As you can see here, in the D forward function, threads are organized to correspond to different layers of the network. N1 threads, indexed by II, handle the input nodes, with one thread per node. M1 threads, indexed by JJ, process the hidden nodes. K threads, indexed by LL, compute the output nodes. The computation proceeds as follows. Each input thread, II, fetches data from the device array D inputs and stores it in the shared memory array X. This step is performed in parallel across all input threads. The hidden threads, JJ, then operate in parallel to compute the pre-activation values, A, and activation values, H, for all hidden nodes. Finally, the output threads, LL, run in parallel to calculate the predicted outputs Y. The backward pass proceeds as follows. Output threads, LL, compute the prediction error and store the result in delta OLL, all in parallel. Hidden threads, JJ, compute delta JJ in parallel, based on the backpropagated error. Weight updates are performed in parallel as well. WO, hidden to output weights, are updated by the JJ and LL threads in parallel. W, input to hidden weights, are updated by the II and JJ threads in parallel. These are routine memory allocation, nothing special. The train member function is responsible for launching the forward and backward kernel functions. It sets up a three-dimensional thread block, as previously described, and passes it to the kernel calls to enable parallel execution across input, hidden, and output nodes. In the main function, we create an instance of the MLP class, which allocates device memory and initializes the necessary parameters. The MLP object then calls its train method to train the network over 10,000 iterations. After training, the model is tested with various input values to evaluate its performance. Let's copy the code into a file, compile it, and then run the executable. Again, we obtain results as expected. 0 exclusive or 0 is 0 0 exclusive or 1 is 1 1 exclusive or 0 is 1 and 1 exclusive or 1 is 0. These are the final weights for reference. Let's look at another simple problem that can be learned by an MLP, the full binary adder. This circuit adds 3 binary inputs, say x1, x2, and x3 and produces 2 outputs, the sum, S, and the carry, C. For example, 0 plus 0 plus 0 results in C equals 0, S equals 0. 0 plus 0 plus 1 results in C equals 0, S equals 1. 1 plus 1 plus 1 results in C equals 1, S equals 1. And so on, covering all 8 possible input combinations. In this MLP setup, we have 3 input bits, plus a bias term, so N1 equals 4. There are 2 output bits, so K equals 2. We'll use 4 hidden nodes, plus a bias, making M1 equals 5.
We could basically use the same program to train the binary full adder. All we need to do is to change some parameters, the N1, M1K, and the weights, and the inputs, and corresponding outputs. Okay. Now let's copy our exclusive OR MLP program to FA, meaning the full adder mlp.cu. So let's make some changes to the parameters. So this should be FAMLP.co now. Okay, so we have to change these parameters. So we change this to this set of parameters. Okay, N1 becomes 4, M1 5, K2, lump sample is 8. Okay, and these are some other random ways. Okay, inputs. Okay, and targeted outputs. Okay, we also need to make some change in the training testing. Okay, so these are the same, but the testing data are different. Okay, so we delete all this. Use the new data set. Okay, so these are the testing inputs. And now let's compile this. MVCC FA MLP.co -O FA MLP. Okay. So it compiles. Now let's execute this. So again, you can see that the MLP program successfully trains the binary adder. It gives the correct outputs, okay, for the appropriate inputs. Okay, like 0 plus 0 plus 0 is 0, 0. Okay, and 1 plus 1 plus 1 is 1, 1. Okay, and so on. Okay, and these are the ways for your reference. So of course you can modify this to train other simple circuits. Okay, and if you feel that this video is helpful to you, please give it a like. Thank you for watching. See you next time.